Hey folks, today we're going to be talking about half-life. Now you learned about half-life back in probably biology or earth science, but we're going to go and make it a little bit more straightforward for you, we hope, just to give you a little bit more information. Okay. Remember that radioisotopes or radioactive isotopes, we use these two names interchangeably. So don't be surprised when I use one or the other. Many elements have at least one radioactive isotope, even hydrogen. There are lots of radioactive isotopes, many of which do not exist in nature, some of which we create. But for example, hydrogen has one proton and it does not have any neutrons. So that's the most common one right there. So it has a mass of 1 and it has one proton. But we can also find hydrogen which has, again, one proton, has to have one proton, but it also has a neutron with it. All right, we call this deuterium. And then we can also have hydrogen that has 2 neutrons with it. This is called tritium. And tritium has a half-life of a few years. Actually, it has a half-life of 12.3 years. So this actually used to be used in watches to make watches. Your watch was actually radioactive, but it glowed in the dark, so that you didn't need a light with it. So that was kind of cool. Back when I was a kid, I used to have a tritium watch, and that was kind of neat. Okay. Anyhow, half-life is, the formal definition is the time it takes for half of a sample of an isotope to decay. So some are very short, right? Some have short half-lives. For example, let's look at uranium. We have uranium, and uranium is number 92. This particular isotope is uranium-226. And this has a half-life of 150 milliseconds. All right, so it's very, very, very short half-life. So in 0.15 seconds, half of it is gone. All right. Now others are very long, so again, we can still use uranium, but we have a different isotope, which is uranium-238, which is very common in nature. And its half-life is 4.5 billion, that's with a B, years. All right, so it takes a real, real long time for that stuff to decay. So remember half-life, the concept of half-life is if I have a brick of something, then after 4.5 billion years, in the case of U-238, only half of that brick is going to exist. All right, and if I go along and spend another 4.5 billion years, only half of that, or a quarter of the original, would exist. And if I kept going, I would say, well, now only 1/8 of the original would exist. Right? So that's kind of the concept behind half-life. Now remember your carbon isotopes, we talked about those in the first podcast, where some things are very stable, like carbon-12, and carbon-16 at a half-life, I believe, of 3/4 of a second or something like that. So again, different isotopes have different half-lives. They stick around longer. But all the carbon, doesn't matter whether it's carbon-12, 13, 14, 15, or 16, they all look exactly the same. They all bond exactly the same. So just by looking at them, you cannot tell one from the other. Let's say that we had the half-life, we looked at rubidium-87, and we said that its half-life is 6 times 10 to the 10th, that's 60 billion years. Now, rubidium-87 becomes strontium-87, so what kind of decay would that be? Well, we notice that the mass is not changing, so that's really a dead giveaway, right? Because if we use an alpha particle, we have a mass of 4 and 2, and obviously we're not changing the mass, so this doesn't work. So it's going to be a beta particle. These are the two that we focus on, are beta and alpha, because your mass of a beta particle, an electron, is virtually 0, and your charge is -1. So we're going to say that this gives off a beta particle with a 0 and a -1. And, well, what's left? Well, our mass didn't change, so it was 87. And our number of protons went up by 1. Remember, it goes up to 38 because one of the neutrons gets converted into a proton. Right, so that's strontium. Right, so that's the kind of decay that goes through. How about carbon? Carbon has a half-life, carbon-14 has a half-life of 5,730 years. It becomes nitrogen-14. What type of decay is it? Well, again, clearly our mass is not changing. And since our mass isn't changing, it's 14 in both cases. It's creating nitrogen-14, We're told it's nitrogen 14 and nitrogen 7. So what's our difference here? Well, clearly that is also a beta particle because our mass didn't change, but the number of protons did. So that's called beta decay. So why do we care about these things? Why do we want to understand half-life? Well, for one, we want to know how long a substance will be around. For example, carbon-14. Okay? Or if we're using something else that we're using for nuclear power, we want to know how long it'll be around and how much energy we can get from it, and hence how quickly we get the energy from it. Okay? Now, we do use it in dating objects with carbon-14, for example. So, how does carbon-14 dating work? Well, in your body, we have bones along with other things. Let's say that this is a bone. Yeah, I know it looks like a dog bone. I don't know how else to draw a bone. I'm sorry, I'm not a biologist. Don't know anatomy very well. There's our bone. Okay? Now, so long as it's in your body, there's carbon being added to this bone all the time. Think about it. There's bone marrow in it, and your bones are growing, etc., etc. So all that carbon is being replaced while you're alive. But when you die, the bone becomes very static, meaning it isn't changing. We're not adding new carbon to it because it's not being replaced because it's not alive anymore. So while we're alive, our carbon-12 and our carbon-13 and our carbon-14 percentages stay about the same. Now, carbon-14 is a very, very small amount. But when we die, the bone stops being replenished. So as a result, the carbon-14 decays. Well, it was decaying all along, but you were replacing it. Well, now you're not replacing it. All right? So over the next 5,730 years, half of the carbon-14 in that bone disappears. Well, realize there's very little carbon-14 in it to begin with. So the bone still looks the same, right? But there's less carbon-14. So if we went and we looked at this bone after 5,730 years, all right, we'd only find half as much carbon-14 in there as when it was alive. If we waited another 5,730 years, or a total of 11,460 years, there'd only be a quarter of the carbon-14 that we started with. All right, and if we waited another 5,730 years, we'd only have an eighth as much. Okay, so that's the way carbon dating works. So what they do is they look back at an old bone or a clay pot or something else that was made using carbon, and they can go and figure out how much carbon-14 is in there now, and hence they can date it to figure out how old it was. All right, let's look at just an example. We have rubidium-87, and we note the half-life is 60 billion years. So the question is, how much is left after a given period of time? Well, after 60 billion years, you're only going to have half of it left. After 120 billion years, that's another 60 billion years, you only have a quarter of it left. And after 180 billion years, that's another 60 billion, we have an eighth of it left. And after another 60 billion years, which is a total of 240 billion years, we only have 1/16 of it left. And we can go on to 1/32, etc. Let's just do that. 300 billion years, we have 1/32 of the original stuff left. All right. Well, how do we look at that? Well, let's say that we started at the beginning with 100 grams of the substance. After 60 billion years, we'd only have half of it, which is 50 grams. After another 60 billion years, half of that disappears, so we've only got 25 grams. Then we're down to 12.5 grams, if half of that disappears. And then 6.25 grams. And then 3.125 grams. You can see how this continues just on and on and on and on. All right. Eventually, you might reach zero, but it will take billions upon billions of years because you're only losing half of it at a time. So that takes a real long time for that to happen. All right. Many, 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 many half-lives. So what we're going to try and do is we're going to try and make this easier for you. So realize the more slowly an isotope decays, the more slowly alpha, beta, and gamma radiation is produced. So that means if we're using it for nuclear energy, if it's really slow, then it's not going to give us much energy. If it's really fast, it's going to give us a lot of energy. However, it's then going to deplete really quickly. We're not going to have as much of it left. All right? Normally, one particle is emitted every time the nucleus of an atom decays. Sometimes it's more, but a lot of times it's one. So when an isotope is decaying as slowly as rubidium-87, it usually poses no danger to us. But if we have something that's decaying at the rate of every second or every 2 seconds or even every 10 or 20 minutes or every hour, that's still producing a lot of radiation very quickly. All right, so how in the world do we figure out all of this information? Well, we tend to use a nice little chart. So if you look at this chart, you'll notice that we have a half-life here. These are our half-lives going down, right? And our time always starts out at 0. And this is something that my students tend to forget to do a lot. Make sure you always start at time 0, because you're told often how much stuff you have. So we're told the original sample, for example, contains 10 grams. Well, this is our amount. It's going to be in grams. We're going to have 10.0 grams of our substance at time 0. Now, we're told that the half-life of plutonium is 45 days. So after 45 days, how much of it will be left? Well, only half of it. So we go down to 5.00 grams. All right, and this time is going to be in days. All right. Now, I'm real lazy. Right? I don't want to have to think back and forth, back and forth, back and forth. So I create this little chart to help me out. So I say, well, 45 days is my first. Then I go to 90. Then I go to 135. Then I go to 180. Then I go to 225. Right now, and I could be really lazy here, up to 270. I notice it says how much is present after 135 days. So I can stop right here. I don't need to bother with all of these down here because I never get there. I'm only stopping at 135 days. Now, remember your half-life says half of it disappears. So if I start with 10, I go down to 5. I then go down to 2.5. I then go down to 1.25. Oh, notice I can stop. I don't even need to fill in the rest of this chart, right? Because I can stop, right? So this tells me that I've gone through a total of 3 half-lives, that it took 135 days, and I have 1.25 grams of the material left. Okay, does that make sense? All right, if you draw this this chart every time, here's another example of the chart, same chart. Right? If you use this chart, and I give you 3 or 4 things, I give you the amount of time that's passed, how much mass you started with, how much mass you ended with, and or the half-life. If I give you 3 or 4 of those, right, I did give you 3 of them. Right? I gave you, in this case, I gave you the elapsed time. I gave you the starting mass. Right? My elapsed time was 135 days. I gave you the starting mass, which was 10 grams. And I gave you the half-life, which I told you was 45 days. Then you should be able to calculate this one. Now, if I give you any 3, you should be able to calculate the 4th. So that's what we're going to do. We're going to go through some examples where I give you different pieces and you figure out what it is. All right? So this is very similar to what the one we just did. Go ahead and pause the video, see if you can figure this one out. All right, did you pause the video? All right, your time is in years, your amount is in grams, and it says our initial mass is 100 grams. Our elapsed time is 151 years, so that's somewhere down here. We don't know where yet. And we're starting with 30.2 years. So let's start with 30.2 years, and let's just keep working our way down here. We add 30.2 every single time, right? Because we go through another 30.2 years. That's a half-life, right? A lot of students, by the way, when you get starting here, they'll take 60.4 and they'll double it to 180.8, to 120.8. You don't do that, right? You're adding 30.2 every time. You're going through that half-life every time again, all right? That's 120.8, and then that's 151. All right, well, you'll notice I got to what I was looking for. There's my 151, right, so I can stop. And I was given my half-life, and I was given the 151, and I'm given my starting amount, which is 100 grams, right? Now, what happens for every half-life? That's right, I go down by half. So that's 50, that's 25, that's 12.5, that's 6.25, that's 3.125, right? So my answer here is going to be 3.125, and my units are grams, and that's what happens in 151 years. All right, let's do another one. All right, we are given our half-life, we're given the elapsed time, the initial mass. Pause the video, please. You should be able to do this one. Please pause it and try it on your own. All right, our initial amount is 18 grams. Our time is in years. This is 5,730 years is my half-life. And I had to figure out I had to go up that far. Well, let's see what I've got. This is 11,460 years, and then 17,190. Great, I'm done. Okay, so I have this number here. I had that number here. I have this number here. So this goes 9, and this goes to 4.5, and this goes to 2.25 grams. All right, so my answer is 2.25 grams at the end of 3 half-lives. All right, now this one's a little bit different. So see if you can figure it out. Pause the video, try and figure it out on your own. If you can't, I'll be happy to help you. All right, our initial mass is 256 grams. We're given that, 256 grams. And we're told that our half-life is 3 minutes. All right, so those are pieces of information that we're given. And our final mass is 4 grams. So we're not given how much time it took. So where do I put the 4 grams? Where does it go? Well, I don't know where it goes. So what I have to do is I have to work my way to that number by doing half-lives. Well, every half-life, half of it goes away. So half of 256 is 128, then 64, then 32, then 16, then 8, then 4. Oh, well, here I am. There we go. That's our final amount. Well, how much time did it take? Well, let's see. Our half-lives are 3. These are in minutes. So this is 6, 9, 12, 15, 18. So it took 18 minutes to get all the way down to 4 grams. You follow that? Again, we're just using the pieces of information we're given and what we understand about half-life. All right, let's try this one for gold 188. It has a half-life of 9 minutes. We don't know what we started with. We don't know our initial mass, but we do know our final mass. All right, go ahead and see if you can do this one. Again, if not, I'll be happy to help. Okay, our initial mass is what we don't know, so we don't know this amount up here. That's what we don't know. We do know that our half-life is 9 minutes. So if that's 9, that's 18, 27, 36, 45, 54, and that's in minutes. Okay, I can fill that part in. And it says my elapsed time was 36 minutes, so there I am, and the final mass was 5 grams. Well, if my final mass was 5 grams, one half-life prior, how much stuff did I have? Of course you had. Of course. So if this was 5, then the thing above it would have been 10, because half of 10 is 5. And half of 20 is 10. And half of 40 is 20. And half of 80 is 40. So our answer here would be we started with 80 grams. That wasn't so hard. All right, let's try another one. We've got 2 more problems to do here. Xenon, go ahead and pause the video. Please pause the video. Do this on your own. All right, our initial mass is 200 grams. Our elapsed time, is 100 hours, so we don't know where that's going to go. Down there somewhere. And your final mass is 6.25. Well, let's see how that works. That would be 100. That would be 50. That would be 25. That would be 12.5. That would be 6.25. Aha! We got there. There's our number. And that took 100 hours. We went through 5 half-lives to go to 100 hours. So how much was each half-life? Gee, it sure looks to me like it would be 100 divided by 5, which would be 20. So let's see what happens if we put 20 hours in here. Let's see what happens. 20 hours, 40 hours, 60 hours, 80 hours, 100 hours. That sure works. Fabulous. All right, you figure that out? Let's go on and try our last one. Again, guys, pause the video, see if you can do this one. All right, our initial mass is 50 grams. Now we have our final mass of 3.13. So let's see how we get there. We get 25, we get 12.5, we get 6.25, we get 3.125. Aha, look at that. There's your 3.13. Right, so let's see. Our final mass is 3.13. Our elapsed time is 24 minutes. We went through 4 half-lives to get there. So what number goes up here? Well, hopefully you were able to figure out that was 6 minutes. Because 6 minutes plus 6 minutes makes 12 minutes. 12 minutes plus 6 make 18 minutes. And 18 minutes plus 6 gives me 24 minutes. What did I do? I took the 24 and I divided by 4. All right, folks. Hopefully you're able to do that. Please go off and do the worksheet. Practice this so that you can do well on the test. And let me know if you have questions, or let us know if you have questions. We'll be happy to help you. Okay? Take care. See you soon.